بسم الله الرحمن الرحيم والصلاة والسلام على رسول الله نبينا محمد وعلى آله وصحبه وسلم. السلام عليكم ورحمة الله وبركاته. First of all, I want to thank everyone for coming to this webinar. I would like to thank the College of Computer Science and Information Systems in Najran University for arranging this event for students, researchers, and whoever might be interested in technology topics. I want to congratulate Dr. Hamad Abusaq for completing his PhD. Dr. Hamad has received his master's degree from DePaul University from the US in 2014. Dr. Hamad has received his PhD degree from the University of Idaho from the US in 2021. Dr. Hamad's main research interests are in software testing, software security, information security, networking and communication, NLP data analysis and processing, data science, and other related technology topics. Today, Dr. Hamad, inshallah, will talk to us about his PhD work, which is titled Using Grammar Extracted from Sample Input to Generate Effective Fuzzing File. Thank you again, Dr. Hamad, for willing to share with us your work. The mic is yours. Whenever you are ready, you can start.
Assalamu alaikum wa rahmatullah wa barakatuh.
Alaikum assalam wa rahmatullahi wa barakatuh.
Thank you for everyone who joined us today to explain my dissertation titling Using Grammar Extracted from Sample Input to Generate Effective Fuzzing File. And the agenda going to be introduction and background, research objectives, contribution, research work, experiment and evaluation, future work and conclusion, then the references. So we are going to start with introduction and background. So the field we are starting from like software testing, and the software testing we know is like process that running program to check whether it is free of defects, bugs, or any kind of security issue, meeting with the specification requirement, and then we make sure that it's executed in the blinded environment as we expected. Then we have testing approaches. There are many testing approaches, but the main approaches we have found, we have functional testing, non-functional testing, and box approach testing, which are black box, white box, gray box testing. So we have that. We have also that testing approach is the traditional fuzz testing, which is the fuzzing. Fuzzing is called fuzzing, which is a methodology of automated testing to generate large amount of random or predefined test inputs. Then that feed into target software in attempt of triggering a vulnerability, which is a security issue or weakness in a program or in a software. The advantage is the fuzzing is automated, fast, easy to use, and no need to access the source code of the tested software. But disadvantages can only trigger bugs at the surface of programs. Required sample input file sheets to be able to test these programs. So we have many types of fuzzing with based on the methodology. There is a symbolic execution, dynamic testing, but we are focusing here in grammar-based fuzzing, which the program that we are using grammars that's going to be extracted from the sample input to test the programs. So the grammar-based fuzzing is a fuzzing technique that will take the input, a specific input format or specification to get correct grammar structure. Then we're gonna use the grammar that extracted from the sample input, and we're going to going after that generate fuzzing input, which have to be passes the parsing stage for the program. By using these grammars, the tool or the fuzzing tool can generate a new user input and apply them to generate a new fuzzing input. And the fuzzing inputs, the new fuzzing input could be any number based on the defined strategies that's going to be used to generate these numbers of the input fuzzing file. Then we are going to test like some programs like has to get like 10,000 of fuzzing inputs and then insert them in the program, trying to get any vulnerability or maybe crash the program. Then the tester will know there is a bug or security issue in the program. So the programs support generating valid input to test program and find interesting bugs. By using the grammars and the fuzzing tool, it will help us to increase the code coverage for the program and reach deeper location in the program. A fuzzing tool will face some difficulties to test the program without the user input format. If there is no user input format knowing before, so the fuzzing tool will not be able to test the program. So the grammars or the format input should be knowing and to be used correctly with the fuzzing tool. So grammar based fuzzing, we have there is many studies limit the format of user input for certain types format, like PDF, XML, HTML. So some tools are required to provide the grammars manually, which is tedious and error prone. So it is the most issue with the previous studies. So there are related word grammar-based fuzzing using mutation, grammar-based fuzzing using machine learning, and there's grammar-based fuzzing using evolutionary computation, and grammar-based fuzzing guided by discovery feedback. Research objectives. We have a question at the beginning. Is there a way to extract grammar from sample input files automatically? So we know there is many programs that have different specification or type. So we have like games, web browser program, photo analyzer, simple program. So is there a possible way to get these to get the grammars automatically from different types of programs? So some programs require structure input. We cannot manually create grammars or extract the grammars and provided it. We can't create like or design grammars rules and provide it to the fuzzer for each program. So there is like hundreds of programs. So we cannot be able to just likely manually creating these grammars that will have more time and will not be able to be correct, or maybe there will be many errors in them. So the objective, we are developing a grammar fuzzing tool then which can learn the input format from these user inputs, producing or generating grammars from input format of each program. Use programs to generate using grammars to generate effective fuzzing input, which can then increase the code coverage in the tested programs. Then learning the command order using Markov chain. The contribution are develop a tool to extract the grammars from sample input files automatically. The research will reduce the human interaction with the fuzzer. The research will provide software developer and software security community and a new improved approach to find vulnerabilities or bugs or any security issue in their programs. So the research work will bring a new conceptual method to the software testing community. The research work. So the research work is divided or consists of three parts. So the first one is the grammar analysis of sample input. Then generating fuzzing files using the extracted grammars, then using grammar chain on top of the fuzzing tool. So first one is grammar analysis of sample input. So first, we have in the right and the left side, we have the input files. We have many input files, like maybe 1,000 of the input files. Then we have the next step, we will find the most used delimiter, like comma, space, or dot, or any kind of delimiter. Then take the first word of each line in the sample input file. After that, we are doing the command analysis. Then we did the sort first word, or that should be a command, count the number of all commands, and then find the final command list. Then after that, we'll do the parameter analysis, which consists of finding the first the parameters or the option comes after the command. So we are going to start with the first step. That we are first looking at the sample input file example here. So most of sample input files require a command like input for the programs that we are testing. So we have like copy, the first line copy, then read dot text, and there is a random string. So we have like a first word which should be a command, and the options or parameters come after it should be like look like parameters that should be extracted. So this shows all the messages are sent from the user to the program. Input contains command and parameters, or command only, or some random string format. Now we are gonna doing analysis for the input. So we have splitting the sample input by the delimiter. Then we are going to take first word from each sample input file, sort the extracted items, then count them to be able to know the most used commands. then we will able to get the real commands based on the counting number. As we have here finding the last final command list, that the most used command in the sample input file. There is a calculated percentage by 10% of the total sample input files to exclude the low counts of the command. So if there is if the number of the count exceeded the 10% of the total sample input files, we consider it as a command. So we'll keep them for further processing. After that, we are gonna analyze the words or the strings that come after the command. So for example, we have the last command here, and the last command in line 6, we have last, then we have two parameters, readme.text and then 10. And then we are gonna extract these parameters, first parameter, then we count them, and if the number of count exceeded the 10% of the total number, the total count of the command last, then we consider it a real parameter. If it doesn't exceeded the 10% of the command count number, we will exclude it. Then we will have here, as we have an example, readme.text, and then authentication.db will be a real parameter, first parameter. Then the 10, we have 10 as second parameter, so we'll consider it as a real second parameter. So after finishing the command and parameter analysis, we collected various commands look like what we have here. We have, for example, arrays number 1. Arrays or 1, which means command arrays has one parameter to come after it. So arrays we have two first parameters, readme.text and authentication.db. And first two, which mean first the command following by first and second parameter. We have two things. We have readme.text and 10 authentication first parameter and 10 is second parameters. And last two, as we see in the last example, has two parameters, readme.text 10 and authentication.db 10, and so on. We have make one, which have make up one parameter, but with the counting and analysis the parameter, we didn't find the first parameter that exceeds the 10% of the command counting number. And here perms2, we have perms2 parameter. We see here there is no second parameter. So that's because there is no second parameter that exceeds the counting number of the command, the 10% of the count number. So we are continuing with the grammar analysis sample input. So after investigating the sample input files, we see there is a numerical values in the sample input files in the parameter. So for example, if we have command here move, and the first parameter R1 and move R4, and we have command move 10 move 1. So there is, that's the parameters R1, R4, and the parameter 10, 1 for move will not be detected or extracted from the previous step. So we have to treat them or change them to R09 or 09. So R09 or 09 will be able to be as common parameters or real parameters that are going to be extracted. So we change the sample input for the parameter in the sample input for that has the numerical value and change them to 09. That will help us to find them and then count them. If that exceeds the 10% number of the counted number of the command, then we'll be able to extract them and include them in the commas. So for example, we have this command permis2. We have the readme text authentication.db. So we detected the numbers that the second parameter is a number for the command permis2. So we include the 09 as a second parameter for readme detect and authentication 0 to 9. Then we updated the grammars rules. So then we are going to move to the generating fuzzing file by using the extracted grammars. So the purpose of this step is to replace a line of an input file each time within your random string. So as we see before, the format of the input file, and then we are going to take it line by line, and then we are going to change the line each time, and then we generate a new fuzzing file. So when we have to change a line, we are going to generate a fuzzing file. So we are going to change the first line with the fuzzing input or fuzzing string. Then we keep the line after it as it without any change. That's because we want to keep the order of the command or the order of the line. So the programs that we are testing is run correctly without any problem. So the order of the command is the important thing to be able to test the program and run correctly. So we have in here that in sample input files look like what we have here as an example. Then we have take the target line, or starting with the first line, and take the first word, then compare it with the grammars that we extracted. And if there is the match, so we have doing the parameter checking if it's the string, like or character, number, symbols, and then substitute the part of a line. We are going to change only the part of a line, like we're going to select command or one of the parameters and then change them or put the fuzzing line with it with different length, and then save the modified target. So after that, we change the bottom line. We are going to save the modified target line and copy other lines that come after it. Like if we have changed the first line, we are keep the line after it as it without any change. If there is no match here, we are going to substitute the whole line with random string or a number with different length, and then we save the line, and then we are going to move to the second line and do the same process again. So the other, we have the random string generator, which has random test number. So the random test number is created for each command. Like for example, we have each command here, come with the first line here. So we are going to have a random test number assigned for it. So for generating testing or fuzzing line. So the random test number is a 3-digit number between 000 and 999. So the digit 1, it means selecting and replacing part of a line. So replacing a command parameter, replacing with a random string in selected position in command or a parameter. So we have the digit 2 or the string types to be generated, so such as letters, numbers, mix of letters, numbers, symbols, hex characters, and so on. And digit 3 is for length of random string. The length is maintaining 2 lists. We have the first list should be selected between this list or the second list. So the first list is like have a different length, and the second list have another larger length. Now we are moving to the using Markov chain on the top of the tool we are created and the previous 2 steps. The problem statements we have, and we found when we are working in the previous 2 tests, we have the tool is limited to the quality of the sample input files, which means the tool is only generating fuzzing files based on the sample input files with the same order of the command or the same order of the lines. If there is only 1 or 2 sample input file, for example, the tool sticks with the command order of them. Because of these problems, the tools only we're going to be visiting the same location or use the same path in the testing program or in the code. So the goal of using Markov chain is learning the order of commands and their probabilities of their occurrence in the sample input file. After that, we have get this information. We are going to be able to use them to generate a new fuzzing files from scratch without using modifying without using or modifying the sample input files at the previous steps. So the Markov chain, here we are using the Markov chain theory or methodology is a mathematical system which is that focus on transitioning from state to another based on the given probability rules of each state. So, which means that Markov chain is a probability system that's going to take to transition from one case or from one state to another based on the probability. So based on the how many commands that how many commands that occur in the sample input file, then we divided this command on the total of the command that we are counting. Then we will gonna generate the percentage for occurrence of that command. Then we will use this command to be able to be selected when we are going to generate a new fuzzing file. So now we are in the beginning. We are first we have to add the RS or random string indicator on the grammars rules here. So some of the grammars, they're missing a parameter. So the second parameter here, we consider it a random string, and we have the first and second random string for each command to be able to get the complete grammar. So the last grammars we have missing parameters. If copy 2, for example, we don't have second parameter. here and here, and we have, for example, make one. We don't have second parameter, first parameter, so we have to put rs or random string as first parameter for make one. And so also we have the permits. We have the same thing. We have the first parameter here. The second parameter is missing, so we have to add a random string rs. So we'll be able to generate different types of fuzzing strings. So here we have updated the grammars with rs or random string for each missing parameters. So we are going to start with analyzing commands by using the Markov chain. So from sample input file, the commands are obtained and sorted. So for example, if tool have command from two sample input file, we have a list or copy list print read write exit and read write copy list print exit as commands from the two sample input file. So we are gonna have two lists, copy list print write exit and read write copy list print exit will be created. So under we add the start patterns and the final pattern. So the start will be in the beginning and the final will be in the end of the lists of each list here. So the tool adds start and final to help generating order of command chain. So the transition probability matrix of the command. So we are using the Markov chain transition probabilities. So the tool will build the transition of probability matrix for each command. So using command transition pair, we have like current command that comes first and then the next command that comes after it. So we have order command like command 1, then command 2 that comes after command 3. So we are gonna create a chain of commands. So if you have the start list, copy list, print, list exit final. So the start, we have the transition pair look like start list, then list copy, start list copy, then copy list, then print, list print list, print list exit, and then exit final. So the command list will have a copy print exit as the next command. So we have a list has current command. We have 1, 2, 3, and the list copy, and then list print to time, and then list exit. So the list has next command copy print exit as next command. So the probability that we have 25% that copy come after the list, and the 50% of print that comes after the list, and 25% for command exit that you have 25% probability that comes after that exit that come after list. We have command copy has command list as the next command at 100% probability. Command print has command list as the next command at 100 probability. So then we are generating a possible order of commands or command chain. It started by start as the current state, and it select next command based on its probability. So we are gonna select the command that come after start based on the probability and keep selecting the next command each time until picked final. When it picked final, then we will stop generating command chain. For example, the visible, or if we have visible of order of command chain will be start, copy, read, list, print, exit, final. So after that, we are gonna discard the start and final, and we're gonna keep the command list, copy, read, list, print, exit. Then we are gonna using them for generating a new fuzzing file. So generating grammar parameter probabilities. So now after we are getting the command chain, we are gonna use the parameter probabilities. We are gonna generating the probabilities for the grammar parameter in the grammar. So we have the grammar here, and we have the command and the parameter. Then we have command list. We have to find match between the command chain and the grammar. If there is a match, we will gonna use. If there is a match, we can change, take the first line and then analyze copy with the second and change it to RS or 09 and all input files found. Then if there is a match, and we have to find the matches and then count until there is a loop going to find any matches, and then count. After finishing, we will able to find the percentage or the parameter of the command that occur. So we have a copy readme dot 50, for example, 56%, and authentication to be 09 is 25% occur, and random string at first parameter and random second 20%. So after counting then the whole number of the parameters occur, it's going to be divided by the total number of the command occurrence. So we'll get the percentage or the probability for the parameters that occur. Then we have going back to the next command and find if there is a match. If yes, we have to another process again. If there is no match, we are going to the next command until we finish the command chain. So after this process, we'll get grammar rules or the grammar parameters with their probabilities. Look like what we have here. Like we have copy 2, and we have 56% that this parameters comes after this command copy, and we have 24% this parameters comes after the command copy, and 20% this line that parameters comes after this copy. So this is what we have in the end. So after finishing the analysis of commands and parameters with Markov chain and finding their probabilities. For example, if we have the parameters, probabilities, and the command chain, we have copy 2 first to and list 0 HK HD as a random command with 2 parameters, and we have these lines. So we have this list. So for each command, start picking a parameter based on its probabilities. Any command does not in the grammar the tool appends or attaches the RS or random string based on the number of the parameters that follow it. So the new line will be in the file format at the following example. So we have the list of the command here. So copy will select the parameter with readme detect RS. For example, it picked this one. So we have 1, 2, and 3. So it picked the first one based on the probability. So, and then we have the first command, same thing. Selected the parameters based on the probability. So we have this command is not in the grammar. So we attach it or append RS 2 times because we have 2 parameters come after it. So we put random string 2 times as first and second parameter. And parameters, we have this line, and we selected this parameters based on the probability and so on. So after that, we're gonna substitute and replace RS with and 09 with the random string. So RS means random string. So RS change it here to random string. And we have the RS or random string here chain. So if we have any 09 or RS, it's gonna be chain with random string, with random length. After obtaining the new input line, so that tool will use them to generate a new fuzzing files. So we are going to use the same strategies and methods, techniques in slide 22 and 23. The experiment and evaluation, we have the DARPA CGC data set. So we have the DARPA Cyber Grand Challenge competition that was developed to explore research on automated vulnerability discovery and patching. The DARPA experimental cyber research evaluation environment was designed by DARPA. So it contains about 250 vulnerable programs, all of them written in C and C++. Each program has at least one vulnerability and is fully documented. So most of the programs came with network traffic files that backup package capture. Then we extracted these packages that there is messages sent from the user to the program. So we extract them and we use them as a sample input file. This backup file record is like interaction with the program. So that data set is now used in many software security research studies. So the evaluation and testing. So testing has been conducting to evaluate the research work. Testing has been conducting using DARPA dataset. The evaluation uses CP Matthias dataset that was ported from DARPA dataset and provided by the Trail of Fish team. It contains about 247 programs. During the testing, there are 12 excluded programs. So there are 6 programs were excluded because of the compilation issue. 6 programs also were excluded because of the programs and running issues. So general experiment setup. After further generate fuzzing inputs, we created a bash or system in bash script for testing that has been developed to test the program with all fuzzing files. So it feeds the fuzzing file to each programs. During testing trials, the output of the program, we are monitoring for core dump or segmentation fault. This means the programs had crashed and found a vulnerability or bug in it. So core dump or segmentation faults happens when an address of variable falls outside the segment that the variable is assigned to. If it occurs or happens that segmentation falls or core dump message will show up, as we have here in this picture. When we tested or running with the test case number, we have a crash, segmentation fault, or core dump for the program with the file name So we have this as an example. So we have created the system that should be detect the core or the crashed programs with and then if code dump or segmentation is detected, it indicates the program has bugs of vulnerability during the testing. So the first thing is we have code here. We have these fuzzing files has crashed the program. And we have testing showing that the program is under testing with this sample with the fuzzing input file. So the following testing have been created and conducted. We have 24-hour test comparing our fuzzing tool with others, experiments with code coverage feedback, adjustment percentages, crash, and code coverage, experiment on fuzzing updated with Markov Chain model. So with 24-hour test, the purpose of this testing is to examine the programs and testing the programs in 24 hours and find crashed programs. The testing entails running each program for 24 hours. The testing for a program is stopped when there is a crash. Otherwise, the testing continue until 24 hours. It tested like 40 programs in parallel every time. The machine that was used has environment of it is a Ubuntu 18.04 operating system, which has 60 cores, 512 gigabyte of memory, and 80 terabyte of hard drive space. This is the super machine that was testing this for about 24 hours each program. After that, we find the 82 crashed programs out 235. So 35% crash program have been found. So comparing our tool with others, so the purpose of this testing is to compare our fuzzing tool with other and evaluate it. So we used the tools AFL, MOPT, Fair Fuzz, and AFL Fast. There are 235 programs had been tested separately, so with different number of rounds. So we have different number of rounds that take about talk about 1 hour each one for each program. So during the 1 hour, the testing will be stopped if a crash or a vulnerability has been detected or found. The machine that was used has a CPU, it's a Ubuntu system, operating system, and it has CPU AMD Ryzen 2920X 12 core processor, and memory is 32 gigabytes. So the result that after testing, that the total number of crash programs. So AFL crashed 45 programs in 20 to 30 minutes as approximate, and AFL fast crash 45 programs and then find most of the crashes between 10 to 20 minutes. Fairfield and MRBT crashed 54 programs between 25-30 minutes, and MRBT 15 between 15-20 minutes. Our tool crashed 79 programs and about most of the programs 5 minutes. Experiment with code coverage feedback. So the code coverage is the measurement or a way for finding the how much of the code was executed based on a standard. So it will help the developers or the programmers to enhance their code under test. It can assist the developer to improve the code quality and give them give them a big picture of how their testing is going and how percentage of the code has been tested. To give the view of how much of the code is covered. So the limitation of code coverage is that it does not guarantee that 100% code coverage is a free bug. So there's code coverage, standard line, code coverage, branch coverage, and function coverage, and path coverage. We use the LLVM curve, G-curve that was used to get the coverage information for each program. It analyzes the code coverage that part of are executed and not executed. So to count how many statements has been executed and gives a percentage of the code that has been covered. So we use dash B as an option that get the branch code coverage with the line coverage. After that, we will get the GCNO file and GCD files that will be generated that will have the code coverage information after testing all fuzzing files by using the tool that will give the lines and branch coverage information. So the goal of this experiment is to examine the performance of the fuzzing tool, find how much of the code of a program has been tested. So it runs a maximum of 2 days for each, or for some programs. Other programs run and stop after finished testing with all fuzzing input fast. So it was a plan that after finding the query, the experiment was to test the program at a time, and I talk about with me like about 2 months or 3 months. Did not start testing the next program so until previous program was finished, and we used this machine and the environment. After finishing the experiment, the average line code coverage is about 65%, and the average branch code coverage is about 71%. So we have found low code coverage, and some, for example, in some programs. So we have this program an example. So we have 18% 0.37 line code coverage, 20% for branch code coverage, and compressed seal we have 0% line and branch coverage, and main.c have 12.87% line code coverage, and the branch code coverage 6.26. So after investigating, we find
Dr. Hamad, sorry for interrupting. You will have less than 2 minutes, and then we will have question, please. So just less than 2 minutes to wrap up, please.
Okay. So we have the problem with the low code coverage, as we can see, because there is some issue with initializing there is some issue with the initializing some variables in the code. So there is a adjustment percentage, and we have the code coverage. We find in the end we find that 10% is the best percentage that increase the code coverage for a program for each for all of the programs that we have been testing. So with the Markov chain, we have tested our tool, and after we developed and updated our system with the Markov chain, we found there is a new seven new programs were found by that were not discovered by our previous study. The future work, we have a large number of fuzzing files from fewer numbers, so we are gonna start to create new fuzzing file from fewer fuzzing sample input file. we can find the new start and final patterns, and we can use the code coverage feedback confirmation to generate fuzzing output for other path or not visited. Testing the fuzzer with other real-world application or data set to evaluate and improve our study. And with the research work we are talking about, and we are the contributions we talked about before. So, any questions?
Thank you so much, Dr. Hamad, for this really interesting topic and very informative talk. So I really thank you for that. We will have a few minutes for some questions or comments from the audience. Please, if you have any question, raise your hand and you can speak or ask the questions. Okay, I'll have a very quick question about some of the implications of your findings, Dr. Hamad. Could you just give us a very tangible example for the implications of your research?
What do you mean?
I'm asking about an implication of your research. How can we simplify it in a very basic context? It looks like there are so many technical issues here.
Okay.
Is there any implication of your research or your findings?
Yeah, for example, we have, like, for example, the problem in our study, there is the previous studies was considered or centered on generating fuzzing files based on the specific grammar or file format or user input format or specification. Like there is specific, most of the studies like concentrate on one or two user input format or specification. So my study based on generating user input format for most of the specification or user input format. It's not considered for 2 or 3 grammars, but bit more in most of the grammars for user input format. We use these grammars to generate more effective fuzzing files that can go deeper in the programs and find the crash or the vulnerability. So after that, we find that our tool that we have created first is limited with the quality or limited with the sample input files that we are using. So we have to find using Markov Chain that we have to analyze the command and the parameter in the sample input file, and we can be able to learn these command and parameters and give the percentage or the probability for each command and parameter. Then we'll be able to generate new fuzzing files from scratch without using the sample input file.
Thank you so much, Dr.
And we are then we'll be helping the software security to find these bugs automatically without using the manually finding crash, without manually inserting the testing test cases by hand. We are doing it like automatically that we're gonna be inserted into the tested programs.
Thank you so much, Dr. Hamad, for
You're welcome.
very clear answer. Thank you so much. Any other questions or comments from the audience? Any questions?
Can I just meet Dr. Yusuf to?
Yes, please, Dr. Hamad.
Thank you, Dr. Hamad, for this nice presentation. I just want, as a dean, to just to say congratulations on your PhD achievement, and we are so happy to have you here in our college. And I wish you all the best, inshallah, in the coming days, inshallah. Thank you, Dr. Muhammad. Thank you, Dr. Yusuf, for this organizing everything, and Dr. Sultan, I think Dr. Sultan Makti, and the others members who join us in this lecture. And in the end, I wish all the best for you and with the success of your future, inshallah. Thank you, Dr.
Thank you so much, Dr. Muhammad. As Dr. Muhammad said, we are happy to have you back, Dr. Hamad, and proud of your great achievement completing your PhD. And thank you so much again for your really interesting and informative talk today. And I really want to thank Dr. Sultan Al-Makti, who has been really helping behind the scene to broadcast this lecture. So again, thank you so much, everyone. Looking forward to seeing you again in our future, inshallah, talks and seminars related to computer science or information system. So thank you so much all. Special thank to Dr. Hamad again. Thank you so much all.
Thank you. Thank you for attending.
Thank you so much, Dr. Hamad. Thanks.
Thank you.